Hopefully that's come up recording. I'm not sure. I can't see the little dot. It says stop recording. Okay, welcome year 9. Today I am going to run through energy changes with you. We've put the lit tasks up this week, so we've got rewatch the webinar. So if you need to rewatch this at a later point, complete the exam question, which has been put on its own Google Slides document this week, along with the big questions. So there's one with that you can self-mark and one that your teachers will mark. Listening to your feedback, we've put them on a separate slide for you in your classroom, so you can switch between this set of slides with the information and those slides. There is the Google form, which you're used to, and I've put in at the bottom, respond to teacher feedback and mark corrections. So we've noticed that you're getting feedback, you might not have been given the time to act on it, so I wanted to put that in for you this week. There is also an extension document that we will have going up for you in a short bit of time. Okay, excellent. Is there any questions on that before I move on to telling you about today's webinar? Nope, okay. Okay, so today what I want to do is just go through a few things from last week that I've picked up on. I've got a webinar poll for you. I'm then going to introduce some content. I've got more webinar polls, and I've also got a task that I'd like you to try during this webinar. Okay, and we're going to try and double switch between the screens. I'm not sure how that's going to work, but we'll see. And then I will show you the exam questions for you to do later in the week or after this webinar. Now, 2 things I've done in my slides to keep you on your toes and keep you engaged in the webinar, because I'm aware that it can get a bit dull just listening to your teacher. So on one slide, there is a cat. The first person to say in the Q&A box that they've spotted said cat is going to get some achievement points, and Miss Boots is on hand to write your name down. On another slide, I've included a spelling mistake. First person to spot the spelling mistake, again, gets achievement points. And this is all going on through the Q&A box, as well as any random questions I might ask during the webinar into the Q&A box, so achievement points can be given. Hopefully we're all nice and clear on that. And as I said earlier, I'm just trying to make sure, pen, paper and calculator. And you'll see I forgot my calculator, so I'm going to be naughty and use my phone. Right. So this is one of the bits that Mr. Collins did with you last week, and I just wanted to make sure that you are all nice and clear that an ionic structure has electrostatic charges, forces between the positive, which would be sodium in this case, and the negative chlorine. Okay, and it requires lots of energy to overcome those forces between the charge. And it's also really important to note that it doesn't have to be an electron to move or conduct electricity. It can be due to the charge on this little chlorine ion. And obviously chlorine is a non-metal, but it can carry charge. So the ion, if it's negative, can carry charge, not just electrons in metals. And I wanted to be clear on that. I also wanted to make sure we get around the muddling of electrostatic and intermolecular. So when we're talking about ionic structures, it's electrostatic forces which are between the positive and the negative ions. Okay, and if you remember back to electricity as well, which is physics, you might have done in year 8, there is an attraction between positive and negative charge. Okay, so that's me just quickly going over that. And then your simple covalent molecules or your covalent molecules, they have weak intermolecular forces, and that word's referring to between the molecules, so between one carbon dioxide in this picture's case and the other carbon dioxide. So the force between them is intermolecular, and that's weak. And these guys have covalent bonds. Okay, so that is me just wanting to go on about that. There was also a little bit, and I thought it was quite clever, of a model on carbon and how many bonds carbon forms. And the answer is going to always be 4 bonds, because it has 4 electrons in the outer shells. Now, I'm aware we've taught you that diamond forms 4 bonds. That's why it's really hard and strong. And graphite, on the other hand, forms 3, and that's why it conducts electricity. And I think that's why a lot of you said it depended on the situation, because graphite only forms 3 bonds. But graphite, or the carbon itself, can always form 4. So I hope that makes it clear that carbon atoms have 4 electrons outer shell, so they can form 4 bonds. They might not do so, but they can. Okay, going to move on to some poll questions now. I told you I wanted to keep you on your toes. So this is question 1. Let me just load it up. I'm launching now. So an ionic substance has a high melting point due to, is it strong covalent bonds, strong ionic bonds, strong electrostatic forces, or strong intermolecular forces? And your keywords, they're going to be ionic. So ionic takes a lot of energy to break those bonds. Which one might it be? Okay, going to give you a few more minutes. Okay. Right, I'm going to end it and I'm going to share the result. And majority of you have got strong electrostatic forces there, but we have got some saying covalent, some saying ionic, some saying intermolecular. So bear with me for 30 seconds because I'm going to bounce back. So this is our ionic structure. Okay, ionic is metal and non-metal. Okay, they have high melting points because a lot of energy is needed to overcome the electrostatic attraction. Okay, I'm going to leave you with that thought for a second. Okay, it's metal and non-metal, strong electrostatic force in an ionic substance. And if you think your covalents are non-metals and things like hydrogen and oxygen, what are they? They tend to be what in the atmosphere? I'm hoping that made sense. If anyone wants to answer that in the Q&A, so I know that made sense, that would be amazing. So what are oxygen and hydrogen, nitrogen? They're examples of, anyone got that? Anyone answering in my Q&A? Oh, I can see Q&A is going. Let's see if Mr. Collins comes back to me there, or Miss Boots.
And we got one person now who's got the right answer in the Q&A.
Awesome.
All examples of gases.
Yeah, thank you very much. So I don't know if I can relaunch the same poll. I'm going to try. Relaunch. Continue. There we go. I can relaunch. Let's see how many of you were listening to that. Hey. You little legends. Oh, by the way, I haven't said well done and thank you for all your hard work over these few weeks, so I'll do that while I'm waiting. Thank you for keep turning up, and thank you for giving it a go, and thank you for being awesome, Year 9. We all recognise how this is a weird time, but you're all doing super duper 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 amazing. Okay, I'm going to give it a little bit longer. Got 60 of you have answered, which is amazing. I'm going to end the poll, and I'm going to show you that. And say thank you for listening to me. It makes me feel really good. And yep, 93% of you got from that was strong electrostatic forces. So well done, guys. Okay, I'm going to move us on to our next poll. So I'll move the slide. So this one, let's see if you were listening to this question. How many bonds can a carbon atom form? And here we go. Poll 2. And launching now. Dun, dun. Maybe I won't do a countdown like a rocket going off. Remember what I said, carbon, what group, well, I didn't say, but what group is carbon in? Therefore it has. Okay, doing really well on the voting here, guys. Really, really impressed. Doobie-doobie-doobie-doo. Excuse my doobie-doos. You know what I'm like in class if you've ever been taught by me for silences. Okay, I'm going to end that one now and share the result. And yep, correctly spotted that it is 4 because they can form 4 bonds. It's not, depends on the situation, because yes, graphite forms 3, but it would be able, carbon is always able to form 4. So just be careful with that one. But well done, everybody. I am going to move on to the third poll, which apparently I forgot to, oh no, it's there. I just forgot to name it. I'm going to launch it and I'm going to change my slide. So why does chlorine have a lower boiling point than iodine? You've had this question before, by the way. The intermolecular forces between chlorine molecules are weaker. Chlorine's more reactive than iodine. Covalent bonds are weaker in chlorine, or iodine is covalent and chlorine is ionic. Well done to those of you who have answered. You can see a little bit of muddling. I can see where you're coming from. You're all doing really well though. Keep it up, awesome ones. So why is chlorine lower boiling point than iodine? Is it to do with the intermolecular forces? Is it to do with reactivity? Is the bonds weaker in chlorine, or is iodine covalent and chlorine's ionic? Okay. Numbers have stopped going up there, so I'm going to end that one. And I'm going to share, and those of you who went for intermolecular forces are weaker, are spot on. That means that chlorine is able to turn into a gas. It boils at a lower point than iodine, and that links into when I was talking about gases earlier. So your covalent molecules are going to be typically, what's it? Brain just had a melt there. Gases, that's the word. Okay, and question 4, and I did mention this earlier, so again, let's hope we were listening. What has to happen for a substance to conduct electricity? Is it delocalized electrons? Is it that it has ions that are free to move? Is it that electrons move between layers? Or is it that it has charged particles that are free to move? Dun, dun, dun. Going to give that a little bit more. Go have a drink of water because I'm talking a lot. Okay, and I'm going to give it till 40 seconds, so a few more seconds just for you to answer. Okay, I'm going to end that one there. I am going to share the result. Majority of you there, it's quite tight, got that it is charged particles are free to move. Okay, so yes, delocalized electrons cause metals to conduct electricity, but it is going to be important that you get that it's a charged particle is free to move, because when we move on to something called electrolysis, we talk about charged particles, so there's a positive and negative, and they can move. Also links in with that idea of melting a substance or making it dissolve in water. So salt is a good example. Salt dissolved can conduct electricity, sodium chloride, but salt solid cannot. And it's because those charged particles become free to move. I may suggest to Mr. Collins that we have to go at this question again next week to see how we're getting on. Right, last question. Oh no, that was my last poll question. So hopefully we're all good with that. There will be some more later. I'm going to move on now to the content. Do feel free to let us know if you need anything explaining at any point. What I want to talk to you today about is energy changes and energy and chemical reactions. And the reason I picked this is because it's all about what happens when we make bonds and when we break bonds, and the energy that is released or taken in during these reactions, and I thought it fitted nicely into bonding, which is all about bonds. Okay, so first thing I need to get across to you is that energy cannot be created or destroyed, only transferred. And you've probably heard that numerous times. You're thinking, why is she repeating it? But it is important because it links into the idea of conservation. So energy will be needed to break the bonds, and I hope you can see my little mouse, but in this little molecule of methane, CH4 is methane, and in these molecules of oxygen. So we need energy to come in to break those bonds, and then when they come together, energy is released through the making of bonds. And you may have heard something about energy being needed and energy being released in biology. So here is one of my questions to the Q&A. What is the name of the type of reaction of photosynthesis that links in with energy? So photosynthesis is what type of chemical reaction? And I'm going back a bit here. So if you're not sure, I am going to go over it later. So don't worry. I can see Q&A is bouncing. Mr. Collins, how are we doing on that one?
Yep, lots of answers coming in and lots of them are correct. I've had 3 so far that are all correct. Well done to those 3.
Excellent. And do you want to give the answer, sir, to my question?
It is an endothermic reaction.
Excellent. So, thank you, sir. So that is an endothermic reaction. So this part of the chemical reaction here, the methane and the oxygen, is going to be endothermic. And this part of the reaction here is going to be exothermic. Exothermic means what, Q&A box? What do I mean by exothermic? And I'm sorry I'm calling you Q&A box. You're not a Q&A box. It's just year 9. What is an exothermic reaction?
Some people, I think, are confusing endothermic and exothermic with aerobic and anaerobic.
Ah, okay. It is biology and I have gone back. So away from biology, simply what is an exothermic reaction? What is happening in terms of energy? Does that help? I'm going to go through this very quickly anyway. I just want to see what you know. Does that help, sir?
Yep, we're getting many more answers to do with energy, and lots of you are at least got the right idea, if not the exact right wording, but I'm really encouraged by what I'm seeing. Well done, guys.
All right, excellent. So this part, as I said, endothermic, so it's going to take energy in. This part here, exothermic, so it's going to release energy when the bonds are made. Now, it is important to note that all chemical reactions are part endothermic because you have to break the bonds, and part exothermic because you have to make the bonds. But they normally swing one way or the other. So they'll either take more energy in or they'll release more energy. But all reactions do both. So I just wanted to make sure you're clear on that. And you'll notice as well, if you were to count the molecules, 1 carbon, 1 carbon, 4 oxygen, and then 4 hydrogen, 4 hydrogen, we always balance out. Okay, so exothermic reactions. Now, I wanted to do this with a load of pictures, basically. Hopefully you can see them all. So an exothermic reaction is where energy is released to the surroundings, and that's a really, really key point. But we also have different types of an exothermic reaction. We have respiration, which I think some of you talked about earlier, so well done. We have combustion, and I've included this equation because at some point you will need to know combustion and incomplete combustion, so I just thought I'd put it there. Combustion, fancy word for burning, and that's where we take a fuel, for example, ethane, methane, add it to oxygen, and then that always releases carbon dioxide and water. And if you think about it, combustion, burning, we do that to get heat so that we can warm up, and that's exothermic because it's releasing heat energy that keeps you nice and warm, especially around now. Another use of an exothermic reaction is hand warmers. A lot of us use these, and you click that little metal piece inside the hand warmer, it starts the chemical reaction, and then you hold it and it releases heat, keeps you nice and warm. And then this one, which I've never come across, but I think camping shops sell them, is self-heating cans use exothermic reactions. So there's normally a little pop at the bottom of the can that you hit, releases a chemical, causes the can to heat up, and it means that if you're out camping in the middle of nowhere, you can have a hot can of chicken soup, a coffee. I've seen 1 can of beans and sausages, but it means you can have nice hot food, which if you're out camping in the cold is always useful. So exothermic reactions release energy to the surroundings. The examples you need to be aware of: self-heating can, hand warmer, respiration, and combustion. Any questions on that before I move on to the next one? Thought I'd give you a few chances here and there just to ask questions if you need to. No, nothing happening. Okay, endothermic reactions. So these are our endothermic reactions, and we have our typical flying saucers. I'm wondering if that chat box is what I think it might be. And these flying saucers have citric acid and sodium hydrocarbonate, that's what this is, or baking soda that you know, inside them. And when you eat them, they mix with the saliva in your mouth and they can actually feel cold. And normally, if I was in a lesson, I'd get you to eat a flying saucer and you'd see that it goes nice and cold. So this is an endothermic reaction. It means it takes energy in from its surroundings. In the case of if you were eating one, take energy from your mouth and you would feel a slight cold sensation. Another use of an endothermic reaction, because that is kind of a use, really cool flying saucers, is the cool pack. Okay, and that's sports pack. So if you have an injury, they're normally ice bags, or you can have an endothermic reaction pack, which is designed to cool you down. This one here is thermal decomposition, and that is also endothermic reaction. It takes energy in to break down the product. And if you think about it, thermal heat, decomposition, breakdown. So you're taking in heat energy to break down your reactant into the product. And then lastly, bottom corner here, we have got photosynthesis, which takes in energy from the light in order for photosynthesis to happen. And I'm just going to check with Mr. Collins or Miss Boots, did anybody spot it?
They did, we had quite a lot spotting it.
Awesome, nice to check we're all awake. Are there any questions on our endothermic reactions before I move on? Don't forget, guys, there is a spelling mistake somewhere. Okay, right, I'm going to move it on then. So this is just me summarising, just to make sure we've all got it. So endothermic reactions, the surroundings get cooler because energy is taken in from them, and an exothermic reaction, your surroundings get warmer because energy is released. And I'm hoping we're all getting that key point. Okay, moving on. So I think this is just me summarizing. Yep, this is just me summarising, so I'm going to click on quick. So reaction is exothermic if more energy is released than supplied, and it's endothermic if more energy is needed, supplied than is released. So that's just in there for you guys for when you're revising. Same as this is just my key points. Exothermic releases energy when they form new bonds. Endothermic energy is needed to break existing bonds with a little picture. So this again is just me summarising what I babbled on about. Okay, and I'm just going to click back to that very, very quickly just to give you a chance to read it and check. And then Mr. Collins and Miss Boots might need to shout at me again. Oh, sorry guys, I just spilled water on my laptop, so that's why that happened. There we go. In case you can't remember, I am quite klutzy.
It looks like Ella Anderson, well done. You were the first one to spot.
Well done. Thank you, Ella. Anyone else spotted it?
Grace He, well done. A couple of anonymous ones. Archie Smith.
Awesome. Well
George
done.
Richards.
No.
Leon has only just spotted the cat meme. Good job, Leon. Freya Peterson, well done. Zach Shears, good job.
Excellent. Awesome. Thank you, guys. It's just me wanting to have a bit of fun, and also it is important as people who I teach and probably everyone else teach to pull us up when we do make spelling mistakes. So correctly spotted there, it should say endothermic and it says endothermic. Okay, so well done. Right, now we're going to move on to bond breaking and bond making. Okay, so this is where we talk about it in terms of numbers in a minute. So chemical bonds can be broken, energy is needed, and chemical bonds can be made. Okay, so this is your typical question that you might get in terms of bond energy making and breaking. And I want to talk you through it. So you're not expected to do this one. I want to be able to talk it through. And I'm just trying to figure out if I can move the cameras, because I don't know if they're in the same place on everyone's screens or not. I've just moved it to the bottom on mine. I don't know if that did it for everybody else. So we've got an equation shown on the board. I'm going to move my mouse, so I hope you can see it over to it. And this is a picture representation of the reaction between this subject here, which my brain is now saying is ethene, yes, and I've just read it there, bromine, and then we make this here. It doesn't matter what's being broken made in this, I just want to show you the calculation. You need to be able to calculate the energy in the product and in the starting products, and then prove that the reaction here is exothermic. Now you'll notice there's a table on the left, And that table tells us the bond energies in this. Now, it's important to note that you have to do a bit of counting on this one. And I'm going to just start writing it out and then show you what I've written as I sort of talk. I will show you my board. So we've got carbon-hydrogen bonds on the left. So at the minute, I'm looking at everything on this side of that arrow, of the reaction arrow. Okay, so first of all, I'm looking at carbon to hydrogen. And if I just count, I've got 1, 2, 3, 4. Okay, so that means I've got 4 of those. And that means I have to do 4 times this number here. I saw a hand go up. I'm not sure if that was a question, Mr. Collins, or...
If they want to put it in the Q&A, if you have questions on this, but let's run it through once first.
And I am writing it, and I'll show you what I've written in a minute. I'm just not sure. Actually, I can show you now. Hopefully, you'll be able to see both. So I've just switched my camera. Hopefully, can you see my whiteboard okay, Mr. Collins?
Yes, miss, we can.
Okay, so I've got carbon and hydrogen, and I counted round, and there were 4. So 4 times 413, and then I will put them into my phone in a minute. And then we've got, you should be able to see also this here. Now, if you look at the table, you can see C double line, which is a double bond carbon, 614. So we've got 1 of those there. So it just count as 1 if you've got a double line. So CC equals 614, which equals. Then I'm going to move to this bit because I've covered that for hydrogen carbons and that one. And I've got bromine, bromine, and there's just 1 of those. So Br line Br equals 193. Okay, and I'll add these up in a minute. That will give me an answer for the left. So I'm just going to put on my board left, hopefully you can see that. And then I'm going to look at the other side, right. Okay, so I'm moving to this side of the arrow, so our product, and I'm going to again count. So carbon to hydrogen, 1, 2, 3, 4. So that's going to be the same as my answer at the top. Carbon to hydrogen, 4 times 413 equals. I've then got carbon to carbon, and I've got 1. But this time I can see there's only 1 line. So that's going to be carbon to carbon line, and then 348, like so. And then lastly, I've got carbon to bromine, and I can count that I've got 2 of those. So carbon to bromine, 2 times, and my screen is cutting that off. I can't see the number. Mr. Collins, can you see that bottom number?
No, miss, we can't. If you move your board slightly to the left and slightly up, we'll be able to see more of the numbers.
Oh, yeah, better?
And slightly to the left, please.
Yep.
There we go. So we can see better now the calculations that you're doing.
Can you see the one on the board as well, like the screen, sir?
The bottom one we can see is the carbon-bromine bond.
Yep, I can't see that number at all on mine, sir.
We can.
What is it, sir?
The carbon-bromine bond, 276.
Thank you very much. I just can't see it. I've got it cut off. Okay, so that is all my numbers. And now I'm going to add them up. Give me a minute, unless someone else has added them up and they want to shout the answers in the doodle.
Yeah, we've had a few people in the chat doing some adding up. They've come to 2,459 for the left-hand side.
2,459. Yeah.
And for the right-hand side, we've got 2,552.
And 52. Excellent. And can you all see that on my board? I don't know. Oh, I'm going to try something. Hang on. Stop share a second. There we go. That makes it nice and bigger. I forgot it goes upside down. Oh, there we go. I've got the final numbers in, hopefully. Okay, so that gives you the 2 numbers. And if you remember on that slide, it said to prove that it's exothermic. And if you look at this number, it is higher than the first number. So that number shows that it's an exothermic reaction because more energy has been released than was taken in with the other number. Now, I know I didn't do all the maths, but it's excellent that some of you guys did. And hopefully you followed how I stepped that through, oopsie daisy, with all the bonds there. So working through how many, counting them, and so on. What I wanted to do, and I'm just going to share screen again, is give you guys a chance to have a go at one of them. Okay, so this question on the board, as I said before, text doesn't matter. So this is combustion, which we talked about earlier. Calculate the overall energy change for the complete combustion of 1 mole of methane in oxygen. And that 1 mole bit, again, don't worry about it. You're typically looking at the left-hand side and then the right-hand side. And at this point, do feel free to throw any questions at us in the Q&A. I am going to switch my camera. Actually, I'll leave my camera up with my little model for you. If you've got any questions, do chuck them to me and Mr. Collins. I'm going to give you a bit of time to have a go. And these are what we've put in your big questions as well and on the Google form. So just you practicing, sir.
Some people are still a bit confused, so let me, sometimes an explanation from another person helps. Some of you have got it and are working through it. If you're doing that, crack on and just ignore me for a minute. Imagine that these molecules that you can see here in this picture, Miss, can you just mouse over the picture? Here, so each of these molecules, imagine they're little bits of Lego, and they're currently arranged like they are on the left-hand side of the equation. I've got 1 carbon and 4 hydrogens arranged in a methane, and I've got 4 oxygens arranged in 2 molecules of oxygen. Oh, Miss has got some molly-mod there, which is demonstrating it really nicely. And you can see on the molly-mod on Mrs. picture that they've got a bond between them. If I want to make what's on the right-hand side, step 1 is break those bonds. I've got to break apart the bonds. Now, each bond has a certain strength and takes a certain amount of energy. Takes a certain amount of energy to break those bonds. When you want to break a carbon-hydrogen bond, for example, it always takes the same amount of energy. I think, is it 413? It tells you. So to break apart that, I need 413 kilojoules of energy for each mole. Don't worry too much about the units. I need 413 energy to break apart that bond. When it makes a bond, it gives out energy, and the amount of energy it gives out is the same as the amount of energy that it takes in. So when it then on the other side, that hydrogen is making a bond with an oxygen, it gives out 464 energy. So it's what we're doing in these calculations is adding up what is the total energy to break apart all those bonds on the left-hand side, and what is the total energy required, total energy that's given out when those bonds on the right-hand side are put together and made. So what we're going to see is if I was to cut all of those molecules on the left-hand side, I need to break apart 4 carbon-hydrogen bonds. How much energy would that take? I need to break apart 2 oxygen double bonds. So 1 oxygen double bond is going to take, is that 436 by the looks of it? So double that. I've got to double that. Thank you, Miss. That's how much energy in total do I need to break apart all of those bonds on everything before the arrow, on the reactants that are going into the reaction. What about then, as a new calculation, what is the total amount of energy that's being released by the products on the right-hand side? Well, I'm forming 2 carbon-oxygen bonds, so I need two lots of the carbon-oxygen bond, and I'm forming, and this is a bit tricky, 2 water molecules. Now, Miss has put 2 water molecules on the board there, and you can see there are 1, 2, 3, 4 bonds in those 2 water molecules. So for the bonds I'm making, I need 4 lots of hydrogen oxygen and 2 lots of carbon oxygen double bond. Some of you are asking about the 2 in front of the O2. That means I've got 2 molecules of oxygen. So you're having to break 2 lots of the double bond. Something that confuses people is the 2 H2O as well. Some people think there's 3 oxygen hydrogen bonds there, but what that means is there are 2 copies of that molecule, like you can see on Mrs. board. The red is oxygen, the white is hydrogen. Yeah, there are 1, 2, 3, 4. If you can see them there, those grey bits. There are 4 hydrogen-oxygen bonds.
How are we getting on with people having a go at it, sir?
People are working through and have got some answers.
Awesome. We'll give it a few minutes. I do have the mark scheme on the next slide if we wanted to.
Wonderful. Some people saying they still don't understand.
Okay. Those who are saying they don't understand, break it down. Have you got exothermic and endothermic reactions understood? So do you understand that energy is taken in to break the bonds? So energy is needed to break these bonds. And then energy is released when we make these bonds. If you've understood that bit, say yes for us. If you haven't understood that bit, say no. Obviously in the chat box. Sir, did we get any feedback on that?
Largely yeses, but there's a few people who still aren't quite sure.
Okay, thank you, sir. Okay, so when chemical reactions happen, you all know that we take something and then we make something. So when we start a chemical reaction, we can provide energy. So energy is needed to break the bonds. And if I just sort of think about it this way, it's taking the energy to pull these parts apart. So energy is needed to break the bonds. Because we've talked about before in ionic substances and in covalent, the bonds are quite strong. So you need energy to overcome those electrostatic forces or those covalent bonds and break them. So energy goes into the reaction to break the bonds. Okay, and then when we make something new, there's an energy released when they come together. So if you think about it, when you put your bits together here, so I'm doing that, energy is released when that happens. Or, as I always think about it, I'm just going to switch my camera. So back to me, energy is released when we make a bond. So if I do that, I'm going to release energy and you hear it in sound, but I'm making a bond there between my hands. If you wanted to think of it in terms of your hands, to pull your hands apart, energy is needed. And then when you put your hands together, you get a clap sound and energy is released. That's sort of one of the ways I cover that. If you wanted to try that with your hands, so put them together, pull apart, you need energy to pull them apart. If you had someone else, you could try and get them to pull your hands apart. Energy needs to go in for that to happen. And then when you clap, put your hands together to make a bond, energy is released in the sound of a clap. Hopefully that's helped that bit. And then when we're talking calculations, you're always given these numbers. So I kind of think of it a bit like a maths problem. And there's some counting involved and then some timesing and adding up. Okay, so basic maths problem. So looking purely at methane here, we've got carbon in the middle. And then there's 4 little lines going round and each line is a bond. Okay, and so carbon to hydrogen there, 1 bond. Carbon to hydrogen here, another bond. Carbon to hydrogen here, a 3rd bond, and then carbon to hydrogen here, a 4th bond. So 4 times 413, because we've got carbon, hydrogen, so 4 of those. Now here it says there's 2 of, so that means there's 2 of these. I haven't got enough molecules to make another one, but there's 2 of them. Okay, so that means because it's got a double thing here, it's 498 times 2, because there's 2 of them. Then you add all that together and that would be the energy needed to break those bonds. Okay, and then on the other side, looking through, we've got carbon dioxide here and we've made carbon dioxide, so energy is going to be released. So carbon to oxygen, there's 2 of them. So that's 805 times 2 because there's 2 of them. And then here we've got our water, H2O. And again, we've got 2 waters. So oxygen to hydrogen, we've got 2 bonds there, but there's 2 of them. So 2 times 2 means I need 4. So 4 of this number at the bottom, which again, I can't see. And then that will give you the answer. I'm going to click it over. Hopefully you can see that. That shows the working for you. So there we've got, again, the 4 times 413 for the methane. Then we've got the 2 times the 498 for the 2 oxygens, which gives you 2,648. And that is a mark if you've managed that all by itself. And then we've got the other side, the right-hand side of the reaction. So 2 times 805, because there's 2 lots of the carbon double bond with the oxygen. And then 4, because we calculated it up, of the hydrogen oxygen bonds, which gives us 3,466. And then underneath that, which I just need to try and move the cameras on my screen, is the final numbers. That didn't help, but we do get a final answer of 818. And because this is combustion and it's exothermic, that means that's the amount of energy that's released. How are they doing, sir?
They're doing pretty well. Some people are getting exactly the right answer. A common mistake seems to be only doing 3 OH bonds rather than 4. That 2 can look confusing. That 2 in front of the OH picture that you've got there, that's 2 of the whole molecule. So there are 1, 2, 3, 4 bonds between oxygen and hydrogen that you need to make. So that, 2 copies of the molecule. So you've got 2 bonds in each molecule, so 4 bonds in total. So if you got an answer of 3002, that's probably the mistake you made, because you're out by exactly 1 OH bond.
Does anybody want more time on this, or are you all right to move on, lovelies? I thought I'd just ask, because we can either try and go through it again or just give you a bit more time to calculate. And I realise, sir, that this is the bit I told them to bring pen and paper and calculators for, but I didn't tell them that at the beginning of this.
Well, just one more time, miss. We're still getting, why is 2HOH 464 times 4? Do you want to explain that one more time?
Okay, so this bit, the 2OH one, the OO one. Oh no, which bit, sir? This one, water.
The water. Why is it 4 OH bonds?
Okay, so this, you will hopefully, I'm going to try and show it with Molly Mods, is water. Okay, hopefully you're all happy with that. Okay, we've got 2 hydrogens and we've got our oxygen. And if you count the little grey bits, they're bonds, and there's 2 of them. Okay, so that is 1 water molecule. The big 2 in front tells us we've got 2 water molecules. So I'll bring in my second. Now we've got 2 water molecules. So if we count the number of bonds, and I'm going to sort of hold them weirdly, we go 1, 2, 3, 4. So there are 4 oxygen bonded to hydrogen bonds in 2 lots of water. And that's why it becomes 4 times 464, because 464 is the energy for your water to your oxygen to hydrogen, and there's 4 of them. So we times that by 4. It's the same on the other side for the double oxygen. This is our oxygen molecule with our double bond.
1 second, miss. They can only see the slide, so let me see if I can change that so they can see
Oh,
you.
okay. I can stop sharing for a minute.
That might be the way to do it.
Okay, so what I was talking about, sorry about that, guys, is this is our water molecule. This is 1 water molecule, oxygen with 2 hydrogens. Okay, and you can see there the little grey bits are bonds, so there are 2 of them. Okay, so we know we've got 2 of them. Now the big 2 in front of H2O tells us there's 2 lots of H2O. So we've got another molecule there of H2O, 2 lots of it. And if you then count the bonds here for 2 lots of it, 1, 2, and then 3 and 4. So that's why we times that bond number by 4. Big number in front tells you how many of that molecule you've got. So big 2 means 2 of them. If it was 3, there'd be a third one. 4, there'd be 4, and so on. Hopefully that's helped. I'm going to go back to sharing screen. There we go. Are there any more questions before I do the last little bit? Because I'm aware of time. And I have planned it so Mr. Collins can also go back over this and we'll see how we're getting on next week. So the idea is not to leave you all hanging and thinking, oh dear God.
So I've resolved all of the questions in the Q&A so far. So
Cool.
Miss, maybe if you want to move on and just recap and show them what the work is this week.
Okay, yeah. Does that mean I don't have time for my last poll, sir?
I think we've got time for a poll.
Okay, I've only got 2 more, I think, sir. I wanted to keep them, you know, with us. Yep, 2 more. This one, 50-50%. So what type of reaction releases energy to the surroundings? As I said before, this point gets really important in physics as well. It's a nice one. Going to give it another 5 seconds. Maybe a few more. Doobie-doobie-doo. On that, on my brain thoughts while I'm waiting, if you have any feedback on stuff you've liked from today that you want to see again, because obviously I've been playing around a bit with the spelling mistakes and cats and more polls and getting you doing something during the webinar, do feedback so we know if you liked it, didn't like it, etc, etc, because obviously this is about how you guys are doing. I'm going to end that poll and I'm going to share the result. Excellent, 90% of you, energy released, exothermic, so well done. Last poll for you lovelies is this one, and this one is a little bit mean maybe, I don't know, we'll see. So which of the following reactions is endothermic? Is it respiration? Is it combustion? Is it citric acid and sodium hydrocarbonate? Or is it ice melting? And the word there was endothermic. And I'll click my slides on as well because I just realised I didn't. I did say this was a bit mean. Going to give you a few more minutes to see what happens with the numbers.
Just while people are answering the poll, some people are asking their practice questions so they can practice these bond energy calculations. The answer is yes. There will be a PDF of a whole load of exam style questions added. Now those questions have more content in them that we haven't covered yet, but you can go through and pick out the ones which look like what we've been doing today with bond energies and diagrams and equations. They're easy to spot, and just have a go at those. The answers are at the end so that you can check whether you've got it right. Now, like I said, there's going to be more in that than you've been taught so far, but we're going to get to a lot of that next week.
Okay, I'm going to end the poll there because I'd like to talk about this one. So respiration is exothermic because it releases energy. That's why we do respiration, so our muscles can use that energy to move. Combustion is burning. So if you think of a fire, that would be releasing energy. Citric acid and sodium hydrocarbonate is the flying saucer. That one is the endothermic one. And then I threw in ice melting as a bit of a meanie because ice melting isn't a chemical reaction. Ice melting is a change of state. Okay, so it might get some energy from sunlight or just temperature of the room, but it is a change of state. There's no chemical bonds being broken or made there. So I was a little bit mean with that question. I think we'll come back to it next week if Mr. Collins agrees to see if you've remembered what I've just said about that. And hopefully tackled this ice melting as a change of state question. But I am aware I was proper mean. Okay, so just to recap then, lovelies, your tasks, obviously rewatch this for the calculations and any of the information. And then I've put on a separate slide document a practice question for you to do, which has got self-marking. There is a bond energy calculation there. Then there's the big question like we've been doing on that same document. And again, I believe there's a bond energy calculation there, which your teachers will mark. We've then got the Google form quiz, which has a bond energy calculation in. We've put a few around the place. And then we've got respond to teacher feedback and mark corrections. So giving you time to respond to feedback there, as well as an extension, if you want more practice, the PDF document that Mr. Collins has talked about, which I will share into my classroom for you guys shortly. Hopefully that was all okay for everyone. I think we've got 2 minutes, so if there is any questions, this is your 2 minutes to do so. I'm going to stop the recording now, if I can find the button. There we go. And if you have any questions, do feel free to ask them while we have 2 minutes.